Okay.
Okay, thank you, Wojtek. And so, yeah, I'm a postdoc here at the University of Warsaw. I work with Dr. Kamiński. And today I want to tell you about some recent results on gravitational collapse in effective loop quantum gravity. Let me get this. All right. Perfect. So let's consider, for starter, the classical spacetime of a black hole. The prototypical example of the spacetime of a black hole formed by gravitational collapse is the Oppenheimer-Snyder model. So we are in spherical symmetry. The star is modeled as a ball of uniform density, and it's given in this gray part in the diagram. And so its geometry will be described by the usual FLRW metric. The exterior, given in white here in the diagram, is just the usual Schwarzschild geometry. Now, this classical picture will no longer be reliable due to quantum gravitational effects whenever the curvature of spacetime gets to the Planckian scale. And this happens in three separate regions in this spacetime over here, which for simplicity I will call regions A, B, and C. Region A is a subregion in the vacuum part of spacetime in the interior of the black hole, but in the exterior of the star, where the curvature reaches the Planckian scale due to the presence of the classical curvature singularity. If we also consider semi-classical effects, we know that the black hole spacetime will not be stationary, but it will actually evaporate and slowly radiate away its mass. When the mass of the horizon becomes Planckian, quantum gravitational effects completely dominate the dynamics of the horizon, and this is what we call region B. And finally, region C is the subregion in the interior of the star when the density of the collapsing matter reaches the Planckian scale. Now, I say that these are three separate regions because, as you can see from the diagram, the onset of quantum gravitational effects in these regions is causally disconnected. So this means that we can study the physics of these regions separately and then check later that what we find is consistent. So this will be the main topic of this talk. The talk itself is divided in three main parts. I will go over the physics of the interior of the black hole, what I called in the last slide regions A and C, in the second part, and I will go over the physics of region B, what I call the physics of the horizon, at the end of the evaporation, in the last part. The first part is instead devoted to the development of a global and smooth coordinate chart for the Carter-Penrose diagrams of the spacetimes I will introduce. Now, given the importance of and the power in visualizing exact solutions of Einstein-field equations of conformal diagrams, it's actually surprising how many of them are usually drawn by hand without a proper coordinate map for it. In fact, this is the Carter-Penrose diagrams I've shown for the Oppenheimer-Snyder model. However, in the literature, the most common ones you will find is something that looks like this one over here. Now, if you're only interested in global causal structure or properties of infinity, they clearly convey the same information. And this is why most times than not, Carter-Penrose diagrams are drawn by hand. You just want to give a quick idea of the causal structure of spacetime without obsessing over detail. However, it's important to remember that there is no explicit coordinate map that you can get to find diagrams that looks like this. For example, it can be shown that in a proper Penrose diagram for the spacetime, you cannot have both an horizontal singularity and a vertical center of the star. You need to choose one of the two. In fact, in this diagram over here, which is computer generated starting from a well-defined coordinate chart, I chose to have a horizontal singularity. And so the center of the star is given by this peculiar looking curve over here. Now, this might seem just like cosmetic in this simple case. However, in more complicated scenarios with possibly non-trivial interior geometries, it is important to always have a proper coordinate map for the diagrams in such a way that we can check if our intuition, possibly built out of hand-drawn diagrams, is actually sound. Take, for example, the case of the complete evaporation of a black hole. So this is the diagram that Hawking originally drew in his paper on particle creation by black hole to represent his proposal of complete evaporation of a black hole. Now, this is a tremendous tool to get across his idea. And so it did a great job. However, it is important to remember that there is no concrete coordinate map or even metric behind a diagram of this sort, and we should not give more meaning to it than it has. In fact, there seem to be fundamental problems in constructing a diagram, a space-time that looks like this one. This notwithstanding, in the literature, it has become somewhat common to just take this diagram or some of the properties of this diagram as a starting point for all sorts of analysis. So we should remember to not give more meaning to it than it actually has. At the end of the talk, I will try to show you that there is another possibility for the end of the evaporation of a black hole, and I will construct a proper Carter-Penrose diagram for it. Now, the spacetimes we're interested in are spacetime of this form. So we are in spherical symmetry. We have a further Killing vector field, which is perpendicular to the angular directions. And so it allows us to write the metric as a function only of the radial coordinate. And the metric takes this form. Now, two famous examples of such metrics are Schwarzschild and Resonant-Nordstrom. We are interested in possible coordinate charts for the Carter and Penrose diagrams of these spacetimes. Now, for Schwarzschild, usually one just takes the compactification, usually done with the tangent function of the Kruskal-Sekeres coordinates. And this is all nice and easy. If we go from 1 to 2 horizons in Resonant-Nordstrom, the first coordinate chart for the Carter-Penrose diagram was given by Carter, and he defined this chart where the metric is differentiable. Hawking and Ellis in their book show that one can actually use the same coordinate of Kruskal-Sekeres in Schwarzschild, so they're adapted only to one of the two horizons to give a map for the Carter-Penrose diagram, but the price to pay is that the metric is now degenerate on the other horizon. This was solved by Hamilton in unpublished lecture notes he has online, so you can find them online, where he generalizes the Kruskal-Sekeres construction to define a map in which the metric is differentiable. Now, if you're only interested in a visual representation of spacetime, these metrics are perfectly fine, they do a good job. However, I will be interested in maps in which the metric has more regularity than these, and so we're interested in generalizing these sort of constructions. Schindler and Aguirre recently generalized the construction by Carter, and so they found a map for a general F in which the metric can be also smooth. And these coordinates are very nice, and they're adapted to give nice looking diagrams in most situations. However, these coordinates are quite complicated and they lack a physical interpretation. What I will use instead are coordinates which are a generalization of the Kruskal-Sekeres coordinates and in which the metric is also smooth. So let me introduce Kruskal-Sekeres coordinates. So the first steps to get there are the same for all spacetime of this form, and they are familiar from Schwarzschild. So given the f, you just can define the tortoise coordinate as the integral of the inverse of f. Given this quantity, you define advanced and retarded null coordinates u and v, and from these you can define all sorts of metrics like Eddington-Finkelstein coordinates or double null coordinates and so on. Now, these coordinates are separately well defined on some of the horizons of spacetime, but they're never defined at the same time on the horizons. So neither of these coordinates is actually a global chart. Now, from these, we can define Kruskal-Sekeres coordinates in several different ways. But a particularly insightful way for what we'll do later is to study the geodesics in Eddington-Finkelstein coordinates. So let's see how this looks like in Schwarzschild. So function f is now takes this simple form, and we can study geodesics in Eddington-Finkelstein coordinates. The ingoing ones are adapted to ingoing geodesics, of course, so this one, and we see that they're simply described by just the v coordinate equal to a constant. However, the outgoing one is given in these ingoing coordinates by this expression over here, and we see that we have a problem over here. You see that for a finite value of a affine parameter sigma, so for sigma going to 0, we arrive here with v equal to minus infinity. So we see clearly the geodesic continues past this horizon, but our coordinate is ill-defined there, and so we cannot continue past it. The opposite happens for outgoing coordinates, where the outgoing one is easily described, while there is a problem with the ingoing one, and we reach u equal to plus infinity for a finite value of the affine parameter. So this is the reason why all the coordinates we've seen before are not global, because either one or the other is not well defined on one of the horizons. Now, this analysis, however, already gives us the solution. Clearly, these affine parameters are a natural candidate for coordinates that are well defined on the horizons and can be continued beyond them. So if you take the leading expression near the horizons of these geodesics and we do this change of coordinates, these new coordinates, it turns out, are well defined on the horizons, and they provide a global coordinate chart for spacetime where everything is well defined. And these are, of course, Kruskal-Sekeres coordinates. A compactification of these coordinates give exactly this diagram I've shown over here. So this is what happens in Schwarzschild. What happens if we go with more than one horizon? So let's consider Reisner-Nordstrom. The function f is now given by this formula over here, and we will only be considering, we're only interested really in the non-extremal case. The same procedure goes well also for the extremal case. We're just not interested. So we can go and study our geodesics, and we see that the same construction happens again, but now the relevant geodesics don't have one term, but they have two terms, of course, one for each of the horizons. So if we're interested, for example, in coordinates that are well defined on outer horizons, we can just do the same transformation we did before, and we will find coordinates that are well defined on these four blocks with a red dot. However, since we are not considering the contribution coming from the inner horizons, this coordinate will, of course, go bad over here. Analogously, we can do the opposite and just define coordinates that are well defined on the inner horizons, considering just the contribution coming from the inner horizons. So the previous one are usually called outer Kruskal-Sekeres coordinates. These are inner Kruskal-Sekeres coordinates. We would like something more general, something that covers more regions of spacetime, like both two consecutive horizons, inner and outer ones. A natural guess would be to just consider both of the logarithms. This, however, doesn't work, at least not so naively. And you see, the problem is that for this to be a good change of coordinate, we need the transformation to be invertible, and so separately monotonic on each of the regions separated by the horizons. In this plot, we have the outer horizon in capital V equal to 0, and the inner horizon in capital V equal to 1. We see that the transformation is monotonic to the left of the outer horizon, in between outer and inner horizon, but it's not to the right of the inner horizon. The problem is that we would like the logarithm associated to the inner horizon to dominate the transformation over here, because this is what the geodesic tells us. However, here, the behavior of the transformation is still dominated by the outer, by the horizon, by the logarithm associated to the outer horizon. So we would like sort of a way to turn off and on these sort of contributions of the logarithm in such a way that we only have the contribution coming from one logarithm close to the region, on the regions adjacent to the horizon and not on the other ones. And this can actually be done using smooth transition functions. So these are functions defined like this, but it's not important. The only thing we need to know is that there are functions that interpolates between 0 and 1, so between off and on, in a smooth way like this. We can use this function to change the coordinate transformation to turn off and on the logarithms as we want, and we see that now the transformation is in fact well defined. It turns out, in fact, that this is a well-defined change of coordinates that gives me coordinates that are able to cover at the same time all these regions, and they provide a good map for it. So now we did only two consecutive horizons. We have an infinite tower of them. What we need to do is just repeat the same transformation for all the tower of horizons, and we get something like this. Now this seems complicated, but it's just the same thing applied all over again. And this turns out to give good coordinates that cover the complete maximal extension of the manifold. And the metric is smooth in these coordinates. And we see that the conformal diagram that comes out of it is very similar to the one we're used to. The only price to pay is that curves of constant radius, for example, are a bit deformed. And we can see these also from the form of the curve of the singularity. But this is not really important.
Excuse me.
So,
Excuse
yes.
me. Are you taking into account melting conditions between Friedman, Robertson, Walker, and Schwarzschild?
So right now we're just doing vacuum geometries. I will come back to the interior of the star and the presence of the star later on.
Okay, thank you.
Thank you. And so these are good coordinates for this vacuum spacetime, resonant Nordstrom. We will be interested in a more generic spacetime with more generic Fs. The formal procedure I've described for this simple setting can actually be generalized formally for any F. The caveat is that we need to solve this integral for the tortoise function in order also to find later on the geodesics in Eddington-Finkelstein coordinates. So we can apply this easily if you're able to solve this integral. Now, this clearly cannot be done for arbitrary f's, but for many f's of physical interest, this is very easy, and it will be doable also for the spacetimes I'm interested in. So these are the coordinates I will use for my descriptions of the black hole spacetime. Now we come back to Oppenheimer-Snyder model. We've seen we have these three quantum regions we want to describe, and we can do it separately. So I will just start from the interior of the star in region C. So we've seen that the classical geometry is given by Friedmann geometry, by the FLRW geometry. We know it, there's only one degree of freedom, is the scale factor. And in this context, the scale factor gives me the physical size of the star, so the physical radius of the star. Its dynamics is given by Friedmann equation. We can solve it, and we get the evolution in time of this parameter in this plot over here. As we know, classically, the star just keeps collapsing until it reaches a singular point of 0 physical radius. Now, borrowing results from the quantization of symmetry-reduced models in loop quantum gravity, we can actually assign an effective metric to this region that takes into account leading order quantum corrections coming from quantum gravitational effects. The line element stays the same, but the Friedmann equation is modified as shown here, with the correction term given in red. Quantum corrections are controlled by this parameter ρc, called critical density, which is just a quantum parameter of quantum nature whose value is Planckian, and it's related to the loop quantum gravity area gap. When the density becomes close to the Planckian value, these corrections will kick in and they will change the dynamics of the Friedmann equation. In fact, we can easily solve this equation and plot here in orange the evolution in time of the scale factor for the quantum corrected geometry. We see that while initially at low densities, the quantum trajectory is pretty close to the classical one. When you arrive at sort of the Planckian scale, quantum corrections kick in. We don't reach the physical radius of the star, doesn't reach anymore 0, but it just reaches a minimum value, and then it bounces back and it starts to expand. So spacetime is now, spacetime, the interior of the star is now completely singularity free, and we have this nice physical bounce. This, of course, for people familiar with loop quantum cosmology, is just the standard loop quantum cosmological bounce applied to the case of a collapsing star. So this is the interior of the star. We can now go in region A, the interior of the black hole in the vacuum part. Classical geometry is given by Schwarzschild, and we can use the same techniques as before to find an effective metric that takes into account quantum correction. It was done for the first time by Kelly and collaborators. We have, once again, quantum corrections in red, and we see that the line element stays the same, but the defining function f is corrected with a term that goes as 1 over r to the 4th. These quantum corrections are controlled by this parameter capital A, which is simply related to the critical density we showed before. We see that this spacetime has the same form I introduced when I was talking about coordinates. So the coordinates we defined in the first part are well adapted to describe the Carter-Perros diagram of this geometry, and of course this is the result we get. Now we see that as capital A is much smaller than the mass squared of the black hole, quantum corrections don't really affect the asymptotically flat region in the exterior of the black hole. However, they do change a lot the causal structure of the interior of the black hole, as we can now see. So we can start from the asymptotically flat region in the exterior of the black hole. We have now two different horizons, an inner one and an outer one. We can enter the outer horizon, and we find ourselves in a trapped region in between an inner and an outer horizon. If we go inside the inner horizon, there is here a non-trapped region where the star undergoes the bounce we talked about in the previous slide. In the future of it, there is an anti-trapped region, which is bounded by an inner and an outer horizon. And in the future of it, there is a second asymptotically flapped region that is the same as the first one. We see that the space-like Schwarzschild singularity is here resolved. There is no singularity over here, and space-time continues in the future of it. In the interior of the black hole, there is, however, still a singularity, this time time-like, which is in this second mirror asymptotic region, non-trapped region. Now, I will argue later on that this singularity is taken care of by the physics of the horizon, what I call region B, but for now, this is just still part of space-time. Okay, now, interestingly, we derive this metric completely independently from the effective metric in the interior. However, it can be shown in this reference over here that this exterior metric is the unique spherically symmetric metric with a hypersurface orthogonal killing vector field that satisfies the junction conditions with the interior metric at the boundary of the star. So this is a very nice consistency check for the formalism we are using. Okay, so this is a very nice physics, very suggestive. However, we are still working with Oppenheimer-Snyder, so we're still working in a highly symmetric and so idealized scenario. An interesting question would be, what happens if we go beyond Oppenheimer-Snyder? So what happens if we consider, for example, the collapse of a non-homogeneous star with pressure? So the classical physics is given by the equations shown in this slide. The line element can be written like this in particular coordinates, often called LTB coordinates for Lemaitre, Tolman, and Bondi. So they're basically coordinates that are comoving and synchronous. So capital R equal to constant gives the trajectories of the fluid, and surfaces of constant time are orthogonal to the flow of the fluid. We have n is the lapse function, epsilon is a parameter that is related to the mechanical energy of each matter shell, as given by the first equation of motion over here. We have conservation of energy given by this third equation over here, which basically just tells us that the evolution in time of the Meissner-Sharp mass is given by the work done by pressure. So this is all nice. When we introduce non-homogeneities, also in the absence of pressure, we have a new classical phenomenon in the gravitational collapse, which is shell-crossing singularities. These are events where the local energy density of the collapsing matter goes to infinity because two different matter shells try to cross each other. There are true curvature singularities, so the curvature explodes in them, but in the standard classification of singularities between strong and weak, they are weak, which basically means that space-time can be continued beyond them, even if they are a singular point. Now, this notwithstanding, if we think that singularities have no place in the physical world, we have a new problem. We have something we need to take care of. Now, the two main sort of proposals to get rid of shell-crossing singularities is either to consider an appropriate and currently unknown equation of state that would prevent the formation of these singularities, or that they will be taken care of by quantum effects. I will focus on this second possibility. And the case of a non-homogeneous collapse in the absence of pressure, so with dust, was recently discussed by several different people. A few collaborators and I have recently generalized the result also in the presence of pressure. Now, this work was actually already presented in these seminars last semester by Luca Cafaro, so I will just give the main results. We have, once again, the quantum corrections for the equations in red, and we see that the only equation that gets corrected is the one for the physical radius r. They are controlled by this parameter delta over here, which is exactly the loop quantum gravity area gap. So it's still related to critical density and the other parameters we introduced before. So this is a system of partial differential equations, which is ready to be integrated numerically as soon as we provide an equation of state for a fluid. Now, this is very complicated. As a first step in this direction, we considered a linear equation of state. This is clearly not physically motivated, but it provides a simple setting to study the interplay between pressure and quantum effects in an easy way. Now, this plot shown over here is the dynamics of a system of partial differential equation for a choice of initial values and the parameters. We've, of course, studied the dynamics for different values of the initial conditions and parameters, and we've seen that the qualitative physics we get doesn't really change much depending on them. So this is this gives the general idea of what happens usually qualitatively. So the plot is color-coded, and we have a higher density for darker regions of the color. We have the physical radius on the x-axis and time on the y. And the black curves you see are just a few trajectories that are evenly spaced of the matter shells, which give just an idea of the flow of the star. So we see that there is no central singularity. The singularity is also here resolved. And we see that the mechanism of resolution is pretty similar to what we found in Oppenheimer-Snyder. So we have shells that initially collapse, they reach a minimum radius, but then they bounce and they start to expand. However, differently, yeah?
So describe the derivative in R.
Yeah, sorry, I didn't say, but prime is derivative in capital R, and the dot is derivative in time. And which is differently from Oppenheimer-Snyder, where all the shells bounce at the same time because there's a lot of symmetry. Here we see that the center is bouncing when the outer part of the star is still collapsing. This inevitably brings shells together and eventually leads to the formation of a shell crossing singularity over here, where there is a dark spot where all the matter shells go. After this happens, the system of partial differential equations breaks down and we cannot evolve the system any further. We can, however, study trapped regions in the space-time. So we have here in red a trapped region, in non-green the non-trapped region, and in blue the anti-trapped region. So we see also here that the physics we get is very similar to what we found in Oppenheimer-Snyder. Shells always bounce in the non-trapped region, and they eventually form an anti-trapped region over here. The shell crossing singularity develops over here. Okay, so we've seen that the physics, the qualitative physics we found in Oppenheimer-Snyder is pretty much the same we can also have in more general cases, so this is consistent. But here we still have shell crossing singularities and we still can make sense of them. So this completes the discussion of the interior geometry of a system. We need to focus on the last region we wanted to study, region B, the physics of the horizon. Now, momentarily, I will switch to hand-drawn diagrams because I want to play a bit with them, and this is what they're for. I will then go back to properly constructed diagrams.
Excuse
Yes.
me. Can you avoid having crossing singularities after quantum bounce?
Sorry, can you repeat the question?
Yeah. Okay. You at some stage you have quantum bounce, okay, and then
Yes.
you have, let's say, evolution of white hole, let's say. And can you avoid having crossing singularities at that stage?
So what singularity could...
Okay, look, in your evolution, you consider let's say that you are, you consider evolution after quantum bounce, okay?
Yes.
So you are considering an evolution of white hole, let's say, okay?
Yes.
And in that evolution, you can have crossing singularities again, okay?
Yeah.
Can you avoid having them?
So yeah, that's the point. No, you cannot avoid them.
So how can you play a game with that?
What, sorry?
How can you resolve the problem?
Yeah, that's the big question. That's what I would like to know, but yeah, we don't know. So the point is that classically, you can always avoid them in the sense that you can make it, you can give initial conditions in such a way that form after the singularity.
Yes.
Have a singularity, it's done. Here we don't have singularity, and so that's a problem because they will eventually form always. So what we need to understand is why they form and what is the mechanism for resolving them. Now, this is not a gigantic problem in the sense that, as I was saying, These are weak singularities, so there are ways to extend space-time beyond them. So what happens is that these shell-crossing singularities will form a shock wave, and we can get a background geometry as the one I showed before, and we can study the evolution of this shock wave in space-time. So this is sort of give a physical meaning to it, but of course, these are still singular events, so we would like to have a better understanding of them.
Okay, thank you.
Thank you. All right, so I was saying, we want to study the physics of the horizon at the end of the evaporation process. As soon as we consider semi-classical effects and the evaporation process, qualitatively, the part of space-time highlighted in gray is something we don't trust anymore because we don't think it's a good representation of what happens in a physical black hole. And if we wanted to describe this region as we did for the interior, so from a first principle sort of construction using effective equations, we would need to consider exactly Hawking radiation in its back reaction. This is very difficult, if not impossible, so this is not something we want to do. However, we are now in a different position than the start. So we already seen what is the physics in the interior of the black hole. And so this suggests us that there is a natural scenario that is consistent with what happens in the interior. And this is that the trapping horizons that arrive in this area over here just undergo a quantum transition like the interior, and they become anti-trapping over here, all within a unique asymptotic region. So this is basically the same thing that one would do with the Hawking proposal of complete evaporation. You just assume that something happened and you try to study what are the consequences, what you can say about it. Now that we have something concrete to base our assumption on, we do this assumption of saying, okay, what I want to describe is a trapping horizon that transitions into an anti-trapping horizon, all within an asymptotic, a unique asymptotic region. And we can say, okay, can we construct a space-time and a geometry that describe this scenario? And this is what we want to do. So to get a concrete metric, we want to completely neglect Hawking radiation. And what we will assume is that this quantum transition of the horizon is triggered by quantum gravitational effects after a certain advanced time v, represented by this line over here. And this will just remain a free parameter of the model. We want a unique asymptotic region, so we want to cut space-time also before we reach infinity, and we do this here with a surface of constant Schwarzschild time. Now, if we're neglecting Hawking radiation, there's really no dissipative phenomena in space-time, so for simplicity, we can assume that the space-time is symmetric under time reversal under the time in which the star bounces. And so we get a mirrored construction also in the future part of spacetime. Now, the part we don't trust about spacetime is exactly the one bounded by these blue lines, so we can just get rid of them. And since we constructed these surfaces to be surfaces of constant Schwarzschild time, they're always isometric, so they can be identified. And this brings us to this spacetime over here, which is known as the black to white hole spacetime. We have an explicit metric in all the sort of white part of spacetime and for the star. So the part outside this diamond with B written on it, this diamond over here is the region where the quantum transition takes place, and we don't have for now a metric for it. Okay, so we played with them. Now we can switch to actual concrete Kite-Perros diagrams. So we've seen that the analysis of these three quantum regions for the Oppenheimer-Snyder model brought us to this black to white hole spacetime over here. The spacetime is explicitly regular. There are no singularities. Of course, we still have a quantum region we need to discuss further. We have no event horizons. We have trapping horizon and anti-trapping horizon, but there is no event horizon. And importantly, we have a unique asymptotic region in the exterior of both black hole and white hole. Now, can we say something more about the physics inside the region B? Do we expect it to be able to give an effective metric and so describe sort of perturbatively the physics inside this region? Or do we think that this sort of quantum transition is completely non-perturbative and we cannot, the concept of classical metric itself doesn't make sense anymore there? Well, initially, the sort of black to white hole transition started assuming that this transition was a sort of tunneling of geometries. And so this would point toward it being non-perturbative. And also, you see, the geometry in the boundary of this diamond is quite peculiar. We have two different sets of horizons arriving in one side, none coming out from the other. It isn't even clear, it wasn't at least clear if it was possible to define a regular metric for this part of spacetime at all. It turns out that it is possible to define a regular metric there. We explicitly constructed one in the references at the top of the slide. And this is actually where having a coordinate map where the metric is smooth pays off, because we found an extension of the metric in the exterior in the interior, and given the high degree of regularity of the metric in the exterior, we were able to prove almost trivially that also the metric in the interior is regular. If we had used degenerate or less regular metrics, we would have then needed to find appropriate change of coordinates to find the regularity of the metric. But this could have been very hard because you see the metric in the interior actually is much less symmetric than the one in the exterior of region B. Because here, of course, for this transition of horizon to take place, the Killing symmetry we have in the exterior needs, of course, to be broken. And so this gives much less symmetry to the metric in region B than in the exterior. This is just a mathematical construction, so we just found one metric which is smooth and can describe this region, but it is not physically motivated by anything, doesn't solve equation that tells us the dynamics of anything. It's just a proof of concept that there are some metrics that that are regular and can be described something that happens inside this region. We don't know if this something is physical. However, it's still interesting to see what happens in this metric. We see over here to the left how the trapped regions behave. So we see that they actually close on themselves instead of touching each other. So we have a bounded trapped region in red, a bounded anti-trapped region in green, and we see we have a sort of tunnel of non-trapped region between the interior and the exterior of the black hole. On the right, we can see instead how curves of constant radius behave, and this is sort of how you would expect them to behave. There's nothing really new to it. What instead if we have a non-perturbative scenario and this metric we found is not physical and there's something else that happens in region B? How do we describe the physics inside of it? Well, this is actually sort of a problem that seems to be tailor-made to be described by any theory of quantum gravity. We have an explicit metric in the exterior of this quantum transition region that depends on some parameters that we don't care. They don't care now, but these are sort of parameters that we want then the physics inside of region B to tell us which one is more probable, which one is better suited to represent the transition. This four-dimensional geometry induces a three-dimensional geometry on the boundary of a region. And so we have sort of the initial and final state of the transition that happens inside this region. So given any theory of quantum gravity that can describe the Hilbert space of this sort of transition, we can define a coherent state on this Hilbert space that is picked on the classical geometry we have on the boundary. And this gives the concrete quantum state of initial and final state for this transition. And then given this state, we can just compute the transition amplitude for this and check all sorts of physics out of it. Now, this is clearly formally very clear, but very hard to implement in reality, even given the state of quantum gravity theories. So we explicitly did this procedure using the spin-form approach for loop quantum gravity, and we arrived at a formula for the transition amplitude W. Of course, this is a very complicated expression. It's very hard to study. There were some sort of first numerical simulations for studying this object, but it's still in the early stages, and so for actual concrete result, we still need a lot of work. Okay, so what I've shown you is that the loop quantum gravity corrected Oppenheimer-Snyder model describes a non-singular bounce of the collapsing star and a non-singular interior where the trapped region transitions into an anti-trapped region, solving the singularity. We've seen that this physics is actually stable under generalization. The qualitative physics we get is the same. although we still get shell crossing singularities, and these need to be studied further. And finally, we've seen that the black to white hole transition gives a natural scenario for the end of the evaporation of a black hole, and we're able to get a concrete metric to describe this scenario and construct an explicit Carter-Penrose diagram for it. And thank you.
May I have a question, please?
Yeah. Sorry, first people in the room.
Suppose we consider non-homogeneous matter field, okay? And so we know that one can choose the initial conditions in such a way that you wouldn't have a horizon, okay? Do you agree?
So we're talking about the black hole horizon, the white hole horizon.
No. Look. You can take in non-homogeneous matter field, okay?
Yes.
You can choose in the evolution of the system initial conditions in such a way that horizon wouldn't be formed, okay? So you would have naked singularity, okay? This is a series of paper by Pankaj Joshi, for instance, okay?
Yes.
So suppose we consider such a case, we quantize that dynamics. So we would have, I guess, quantum bounds. And after that, the system would evolve towards it's a classical system, something corresponding to, okay, we would expand. And the question is, would we have, however, formation of, let's say, horizon in that evolution or not? Do you know that?
Okay, yeah, no, I'm not sure, but so what you said, I think is correct. I'm not sure what would happen. I guess that if there are situations classically where the trapped region doesn't form, and we would have a naked singularity, the quantum effects would resolve them. I'm not sure horizon form at all, I guess, but I haven't
But
checked.
after bounce, after quantum bounce, would we have horizon, sort of horizon or not? Or still would have evolution of something corresponding to white hole, let's say, but without horizon?
I'm not sure. Most of the models we studied for now are usually pretty much time symmetric. So if there is no trapped horizon or a trapped region in the past, I wouldn't expect an anti-trapped region in the future. But these are very simplified models, so I guess it is possible in more physical situations, especially with non-homogeneity. So there could form an anti-trapped region, but I'm not sure. I haven't checked it.
May I have second question, please?
Maybe in a moment.
Sorry?
There are some questions here live. When we get to those, we can get back to you.
So what's the transition happening? So it is a probability happening. So it's a probability of what factor?
Yeah, so it is sort of a probability. We have this parameter space of free parameters in the geometry in the exterior. So it depends on the mass of the black hole. This sort of t is the time that an observer very far from the black hole, the proper time it experiences from the moment in which the black hole is formed to the moment in which the white hole is formed. So this sort of gives the lifetime of the process. And so the probability would be sort of give us a conditional probability on what sort of combination of these parameters would be the most probabilistic one, the most probable. So if we have sort of a big mass, this t needs to be very big, or the opposite, and so it would give us sort of what is the combination of these parameters that is the most probable.
The question is pretty detailed.
Yeah.
But so the black to white hole transition, yeah, it seems that the space-time is symmetric under the time translation. In times
Time reversal.
yeah. So, but this is not the case for the pair. You want to have like smaller symmetry, especially for pairs, it could induce the change of the axis rotation and direction of rotation of the black hole. So the kind of this was at least qualitatively to break the angular momentum conservation in the system. So
Yeah.
it works for a simple factor case, but this is, can you comment on the physicality of the process?
So yeah, clearly,
It's a big problem. I asked the same question of Carlo, and he didn't have any good answers, so it may be difficult to question.
yeah, no, I don't have any good answer either, but this is clearly a big problem we are working on. Like, we want to generalize this model also to care, and it's not easy, so we need to find a way to do it. But so the assumption of sort of time reversal over here is done for simplicity, but in this simplified context, it is possible to construct a space-time which is not symmetric and then time reversal over this time of the bounce over here. In care, there are other problems, so that's not the solution for that, but this is not an important assumption for this model. In care, there's many more difficulties, as you were saying, so we still don't have a solution for that.
Because I understood that it is, you kind of want to apply it to this, like the black holes that are forming from the gravitational collapse, so they are asymptotic care, more of care rather than.
Yeah, clearly, no. If we want to give actual physical sort of representation of black holes, we need to go to Kerr. We cannot stay in spherical symmetry.
Thank you very much.
Thank you.
Nice result.
Okay, so we can go back to the people on Zoom. There were some more questions.
Yes, so may I have second question, please? Can you hear me?
Yes, we can hear you. You can go ahead.
Yeah, look, again, let's come back to the case we have naked singularity. So does it make sense to talk about Hawking radiation in that case?
So I completely neglected Hawking radiation except for the fact that it exists and we want something to be able to describe what happens at the end of it. But for the actual metric, I did not take it into consideration, which is very hard to do. So
Okay, thank you.
thanks.
Oh, that's thank you.